Hello, fellow chemists. Jolly here. This discussion is going to be on octets. Now, we're going to be using octets for Lewis structures, so this is going to talk about how many electrons you can put around an individual atom. Now, let's go back just to those valence electrons really quick. So I had hydrogen, helium, and remember, we're not doing the metals because this is covalent bonding, so I'm going to jump all the way to boron, and carbon, nitrogen, oxygen, fluorine, and neon. And then you would start over again as you went further down. All right, those are the valence electrons for those individual atoms. And then I talked about bonding places. So boron has 3 bonding places, carbon has 4, nitrogen has 3, 2, 1, and 0. All right, now the question that I'm looking for right now is how many electrons can the nucleus of that specific atom hold on to? And that is called the octet. Now that implies the number 8, which is a little misleading. All right, an octet is how many electrons the atom can hold. All right, so let's take a look. So for hydrogen and helium, do you notice they're in the n equals 1 shell? So they're not very big. Hydrogen only has 1 electron and 1 proton, and helium has 2 electrons and 2 protons. So their octet, so for hydrogen and helium, their octet to be completely full is 2 electrons. That's the maximum that they can hold on to. All of these guys are in the n equals 2. So boron, carbon, nitrogen, oxygen, fluorine, and neon, they are all in the n equals 2, and the maximum they can hold, if you look at neon, the maximum it can hold is 8 electrons, and that's where the term octet came from. Now, if we go down, remember aluminum is a metal, so we're going to go to silicon, and I'm going to draw silicon. Silicon looks just like carbon, but it's in the n equals 3. So we've got n equals 2, and then the one next to silicon is phosphorus, which looks just like nitrogen. So these two are in the n equals 3, but silicon isn't quite big enough. It doesn't have enough protons or effective nuclear charge to hold on to any more than 8. But when you get to the n equals 3, so phosphorus on, it has to have at least 8, but can expand. And you're asking, well, where's it going to expand to? It's going to use its d orbitals. So remember, the location around the individual atom, the individual nucleus, is in shells, and then that shell is broken up into subshells, and that subshell is broken up into orbitals. Well, these guys only have an s orbital, and therefore the most an s orbital can hold is 2. These guys have a p orbital, and the most it can hold is 6 plus the s orbital, which is 2, for a total of 8. All right, now silicon actually has the P, the S, and the D, so it technically could hold 6 and 2 and 10, but it's not big enough. It doesn't have a big enough effective nuclear charge, so it gets 8 and only 8. But down here, you have your S's, you have your P's, and you have your D's. You can expand. All right, so let's summarize. Hydrogen and helium, their octet is 2 and only 2. All right, let's take a look at this little boron. Boron should have 8, okay, because it is in the n equals 2 shell. But if you will take a look up here, poor little boron doesn't have very many protons. In fact, if you'll notice, its octet is going to be 6. So its octet is only 6 electrons because of its size. So it should be able to hold 8, but it can only hold 6 because of its size. But carbon, nitrogen, oxygen, fluorine, whoops, that's supposed to be a neon. Neon, and then silicon all can have 8. So I'm going to rewrite this. I'm going to clear this out, and I'm going to make a octet list for you. Alright, here's our octet list. Hydrogen and helium. The octet is 2. Boron, the octet is 6. Keep in mind, it should be able to hold 8, but it does not have enough protons to do so. Carbon, nitrogen, oxygen, fluorine, neon, and silicon is 8 and only 8. And then anything phosphorus and on, at least 8. But it can have more. Now, how many more? Now, the answer to that question is a little harder to talk about, but it's based on the ability to hold on to those. So the more protons you have, the bigger it can expand. But very typical in expansion is 10, 12, and 14 electrons. Those are very typical. All right, now, what in the world is she talking about? If you haven't done a Lewis structure, it's a little vague. So I'm just going to do a Lewis structure. Keep in mind, this is one piece of the Lewis structure. So if you haven't learned all the pieces yet, it's not going to make much sense. But I'm going to draw a carbon right here. And I'm going to draw 4 bonds. And those 4 bonds represent 2 electrons each. When I'm talking about the octet is everything it owns and anything that it is sharing. So if I do a little squiggle right there, the carbon owned that. That came from its valence electron. This one is being shared. It came from another atom. And so each of these bonds is going to be the same thing. So there are 4 electrons that were owned, and there are 4 electrons that are shared. And if you add them up, that's a total of 8 electrons, and that is called the octet. That is called the octet. All right, so I'm going to draw a few more just to practice here. So carbon has an octet of 8. So let's take a look at this one. So if I have this carbon, what is its octet? All right, so 1, 2, 3, 4, 5, 6, 7, and 8. So this octet is also 8. Now, if you were to draw a little line here, it owns 2, 4, 5, and 7 for a total of 4, and it is sharing 1, 3, 6, and 8 for a total of 4, and so its octet is 8. Another variation. Oh, before I do that, this is a single bond because there's only 2 electrons. This is a single because it's 2 electrons, but this one would be called a double bond because it's sharing 4 electrons in 2 lines. All right, let's try another one. Carbon, like that. All right, I'll number it a little differently this time. 1, 2, 3, 4, 5, 6, 7, and 8. So it has 8 electrons. Its octet is complete. It owns, or came from its valence electrons, 1, 2, 3, and 4, and it is sharing 5, 6, 7, and 8 for 4 electrons, for a total of 8 electrons. All right, let's try another one. Let's try an atom other than carbon. So let's take a look at boron. All right, 1, 2, 3, 4, 5, 6. So there are 6 total electrons around it. Is that correct for boron? And the answer is yes, because its octet is only 6 electrons. So that one is correct. But how about this one? How many does fluorine own? 1, 2, 3, 4, 5, 6, and 7. And how many is it sharing? 8. So it has a total of 8 electrons. Where are they located? There's 3 lone pairs, and there's 1 single bond, for a total of 8. So that octet is complete. That octet is complete. And now let's do an expanded one. All right, so let's take phosphorus. All right, so if you'll notice, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's 10 electrons in the octet. Are you allowed to have 10 electrons in the octet? And the answer is it in the n equals 3? And the answer is yes, so it can use the d orbitals. So yes, it can expand. So the number 10 is an accurate and a correct octet for this phosphorus. And then let's just draw little squiggles. Phosphorus had 5 valence electrons. Do you see them? 1, 2, 3, 4, and 5. Okay. And then how many is it sharing? 1, 2, 3, 4, and 5. All right, and that's how you would do an expanded octet. So a nice review. Hydrogen, helium, 2. Boron, 6. Carbon through silicon, 8 and only 8. And anything phosphorus and on can expand, but at least 8. It can't have less. All right, that is a nice discussion of octets, and I will talk to you next time. Jolly out.